Hello students, welcome to this lecture on approximate methods in quantum chemistry. I am Gopala Krishnan. I am a faculty in the Department of Chemistry, DG Vaishnav College. We know that for a system containing more than one electron, whenever system contains more than one electron, then the Hamiltonian consists of electron-electron repulsion term. Whenever Hamiltonian contains electron-electron repulsion term, then it is very difficult to solve the Schrodinger equation H psi equal to E psi. Schrodinger equation cannot be solved. So, what is the alternative for this? The alternative is we can go for approximate methods in quantum chemistry. So, by using some approximate methods, it is possible to solve Schrodinger equation, and we can also calculate the energy. Right. So, in the case of system containing more than one electron, it is very difficult to solve Schrodinger equation. Therefore, to solve the Schrodinger equation, we adopt certain approximate methods. The approximate methods which are widely used in quantum chemistry are: number 1, variation method; number 2, perturbation method. Apart from this, we have other approximate methods, but in quantum chemistry, these two are the approximate methods widely used for solving Schrodinger equation. Okay, let me start with the variation method. I will give you what are the steps we should follow in a variation method, and how to calculate energy, and how to compare that energy with the experimental result. Okay, so let me start with the variation method first. Variation method. Okay, what are the steps we should follow in variation method? In variation method, for a given system, I have told you already, the system that we are handling contains more than one electron. So, for a given system, according to variation method, first we should guess a wave function. Okay, so we should guess a wave function which is called as trial wave function. We should guess a trial wave function, then we should calculate the expectation energy which I am going to represent as subscript E using the trial wave function. And this is another important information. While guessing trial wave function, you should guess the trial wave function containing certain parameters called variation parameters. So, the trial wave function may contain one variation parameter or may contain two variation parameter. It depends upon the trial wave function that we choose. So, first guess a trial wave function, then using that trial wave function we should calculate expectation energy. As we all know that expectation energy can be calculated using the formula integral psi star trial Hamiltonian operator into psi trial d tau over integral psi star trial into psi trial d tau. So, using this formula we can calculate the expectation energy of the system, but now the expectation energy that we calculate depends upon the variation parameters alpha, beta, gamma, etc. So, what we have to do? We have to minimize the expectation energy so that we will get the ground state energy, possible ground state energy for the system. So, how to minimize? For minimization, we should differentiate this E with respect to the variation parameters that we have chosen here. So, suppose if the trial wave function contain only one variation parameter alpha, then differentiate E with respect to alpha, put that value equal to 0. If you put this value as 0, then we will get the variation parameter, a particular value of variation parameter at which the energy of the system will be very, very low for the chosen trial wave function. So, for the trial wave function, for the particular trial wave function, we will get a particular value of alpha. For that value of alpha, we will get a minimum possible energy for the system. Now, what we have to do? Substitute that value of alpha in the expectation energy formula. So, substitute this value of alpha in expectation energy formula, you will get the expectation energy or the ground state energy, which is calculated using variation technique. But this expectation energy is actually for the trial wave function that we have chosen. Suppose whether the trial wave function chosen is correct or not, in order to identify that, what we have to do? We have to compare this calculated energy with the experimental energy that is available. If the calculated energy and the experimental energy matches, then the trial wave function chosen can be considered as the true wave function. If the calculated energy deviates from the experimental energy in a larger extent, then what we have to do? We have to choose a new trial wave function and we have to undergo this calculation once again. Okay. So, in variation method, we have to choose many trial wave function and we have to calculate the minimum possible ground state energy. Okay. And according to variation theorem, the calculated ground state energy from variation method will be greater than the experimental value of energy, experimental ground state energy. Very rarely it will be equal to the experimental value of energy. When we will get exact value? The exact value is possible only if the trial wave function is the exact wave function for the system, right. So, these are all the steps we should follow in variation method. Now, I will show you how to apply variation method with an example. Let me take a known system, say hydrogen atom. Hydrogen atom is a one electron system. Hydrogen atom is a one electron system. For this, we can solve the Schrodinger equation exactly. But now what I am going to do, whether variation method results are acceptable or not. Okay, how to analyze that. So, for that purpose, I am going to take hydrogen atom for which the wave function, the exact wave function is already known. So, I am going to take that wave function as trial wave function and I am going to calculate the energy. Now, then what we have to do? We have to compare that energy with the experimental result, okay. And I am going to show that in this case the variation method gives exact value of energy if we choose the trial wave function as the exact wave function, okay. So, this is actually a known system. For this, I am going to take the trial wave function as trial wave function. I have told you already, while choosing trial wave function, your trial wave function should contain at least one variation parameter. So, for this purpose, I am going to take the trial wave function as e power minus alpha times r. Okay, we know very well energy in the case of hydrogen atom, in the ground state the electron is present in 1s orbital. So, for 1s orbital wave function, okay, the trial wave function is nothing but e power minus alpha r, where alpha is the variation parameter. Now, using this trial wave function, we have to calculate the expectation energy using the formula. I have given this formula already, psi star trial Hamiltonian psi trial d tau over psi star trial to psi trial d tau. Using this formula, we can calculate expectation energy. I am not going to give you the entire steps of simplification of this energy problem, but I am going to instead I am going to give you the final expression for energy. E is equal to alpha square minus 2 alpha by 2. Right? If you substitute this trial wave function here, and if you do calculation, finally we will end up with this result. This is the energy calculated using variation method. But this energy consists of alpha. Okay, listen, this is very, very important. As alpha increases, we plot expectation energy versus alpha. As alpha increases, the expectation energy decreases and reaches a minimum. After that, it will increase. So, at one particular value of alpha, the energy become very, very low. Okay, so to find the minimum possible energy, we have to differentiate E with respect to alpha. So, what I am going to do for the minimization of energy, I am going to differentiate E with respect to alpha. So, if you differentiate this, keep 1 by 2 as such. If you differentiate alpha square, you will get 2 alpha and minus 2. Take 2 as common, and if you cancel this, you will get alpha minus 1. Then to get minimum possible value, put dE by d alpha as 0. Put dE by d alpha as 0. If you put dE by d alpha as 0, so we should substitute alpha minus 1 equal to 0, and we will get alpha as 1. So, if I substitute in the place of dE by d alpha, if I substitute alpha minus 1, we will get alpha minus 1 equal to 0 or alpha is equal to 1. What does this indicate? It indicates that at alpha equal to 1, the expectation energy goes to the lowest possible value for the chosen trial wave function. Okay. If I substitute this alpha in this expression, I will get the ground state energy possible for the system using for the trial wave function that we have chosen. So, the ground state energy for hydrogen atom can be given as alpha value is 1. So, 1 square minus 2 into alpha value is 1 by 2, which gives the answer as minus 1 by 2 in atomic units. We know very well, if you solve Schrodinger equation for hydrogen atom and if you calculate the ground state energy, we will end up with the same answer minus 1 by 2 atomic unit, which this indicates that variation method works perfectly for systems, for known systems. So, we can go with the variation method for system containing more than one electron system, Okay. Now, so I have proved that variation method works well for known systems, and we can apply this technique even for system containing more than one electron. Okay. Suppose let me choose another example, say helium atom. Helium atom, the ground state electronic configuration, is 1s2. So, both the electrons are present in 1s orbital, and we know very well, right now we do not know what is the wave function for 1s orbital of helium atom. From hydrogen atom solution, we got the wave function for 1s orbital, 2s orbital, 3s, 2p, x2, pz, everything. That is applicable only for hydrogen atom. But if you go beyond hydrogen atom, okay, then it is we never know, or we do not know what is the wave function for the other orbitals. Okay. So, right now we do not know what is the wave function for 1s orbital of helium atom. For that purpose, I am going to choose some approximation method. Okay. The first approximation that I am going to apply here is orbital approximation. Okay. To guess the trial wave function, okay, or to guess a wave function for helium atom, right, I am going to apply the orbital approximation technique, according to which I am going to write each electron with a wave function called one electron wave function. So, for electron 1, let me write as 1, electron 1 present in 1s orbital. Listen, for helium atom we do not know what is the wave function for 1s orbital, but what I am going to do, I am going to take hydrogen atom 1s orbital wave function here as the trial wave function, and I am going to proceed. So, this is 1s orbital of hydrogen atom. Similarly, I am going to take for the second electron, I am going to take the 1s orbital of hydrogen atom. Since both the electrons are present in 1s orbital, I am choosing the wave functions of 1s orbital of hydrogen atom. Okay. Multiply these two, this product is taken as the trial wave function for our system. Okay. Now, if you use this trial wave function and if you calculate, okay, so now I will apply another, so according to which, according to orbital approximation, the electrons are independent. Okay, that is why we write electron 1 wave function and electron 2 wave function separately, right. So, using this approximation, if you calculate energy, okay, this is approximate energy, right. Electron 1 is present in 1s orbital of hydrogen atom. So, for hydrogen like species, we calculate energy using this formula minus Z square over 2n square. Okay, this is for electron 1, plus in a similar manner we have to calculate the energy for electron 2, right. This formula is applicable for hydrogen like species. So, if you assume the 2 electrons of helium atom, okay, in helium atom, suppose assume that this is electron 1, this is electron 2, if the 2 electrons are independent means there should not be any repulsion or no other interaction should exist. Okay. If the 2 electrons are independent, then you can assume one electron with the nucleus as one hydrogen like species, another electron with the nucleus as another hydrogen like species. So, if you assume the 2 electrons behave like independent, then we can calculate energy of each electron using the hydrogen like energy expression. Okay. So, for helium atom Z value is 2, so 2 square is 4, so minus 4 over 2 into principal quarter number is 1, so 1 square is 1 plus minus 4 by 2 into 1. So, if you simplify this, you will get the answer as minus 4. Okay, 4 by 2 is 2, 4 by 2 is 2, so you will get minus 4 atomic unit, and if you convert atomic unit into electron volt, you will get the answer as minus 108.8 electron volt per atom. But if you compare with the experimental result is minus 79 electron volt. So, there is a huge deviation exists between the experimental value and the value which we calculated using independent approximation method. So, what we are going to do in this case, we are going to take this trial wave function and we are going to apply variation technique to calculate the ground state energy of the system. Okay, so how to carry out variation method for helium atom. So, if you apply a particle independent model, if you assume the 2 electrons are independent, then we will end up with the result minus 108 point electron volt, which is definitely far away from the experimental value. Therefore, we cannot use this method for calculation purpose. So, what I am going to do, I am going to apply variation method for this system. Okay. So, this is our trial wave function, So, the trial wave function can be given as 1s orbital of hydrogen atom, which is z by root pi into e power minus zr by a naught. I will take this as electron 1. So, zr1 a naught is the Bohr radius, the constant. This is for electron 1. For electron 2, z by root pi into e power minus z r2 by a naught, where r1 is the distance between the nucleus and electron 1 and r2 is the distance between nucleus and the electron 2. Now, if you use this trial wave function and if you calculate the expectation energy, we will end up with the if you use this trial wave function and if you calculate the expectation energy is equal to, this is the formula, integral psi trial star h operator psi trial d tau over integral psi star trial psi trial d tau. If we use this formula, or if you apply the trial wave functions here, you will get the expectation energy which comes out as 27, okay, I will write roughly 5 by 8 alpha, okay. And if you calculate, if you minimize the energy and if you calculate after minimization, you will get the energy which is roughly minus 77 electron volt. Okay, you know well experimental result is minus 79, but if you apply variation method, you will get energy which is very close to the experimental results. So, it means the variation method works well for system containing more than one electron. Okay. So, this is the basic idea regarding variation method. Now, let me go introduce the second approximation method called perturbation method. Yeah. The second method is perturbation method. In perturbation method, we have we classify perturbation method into two. One is perturbation method for non-degenerate states, and second one is perturbation method for degenerate states. Okay. And in perturbation method, we also classify perturbation method into two, depending upon whether it is time dependent or time independent. So, we have time independent perturbation method or theory, the other one is time dependent perturbation method. Okay. So, let me take time independent perturbation method and I will apply time independent perturbation method for non-degenerate states. Okay. So, how to proceed? Right, listen, this is the idea. First, let me give you what we have to do in perturbation method. Suppose if you want to calculate energy and wave functions for the states for your unknown system, we must choose a known system which is very close to the unknown system. Okay. What is known system? Known system is one for which the energy and wave functions are already known. Okay. Exact solutions for wave functions and energies are available, okay, for the known system. Okay. So, what I am going to do, if you want to calculate wave function and energy for unknown system, I will take this as unknown system. Okay. What we have to do? We should choose a known system. What is meant by known system? Known system is one for which energy, wave functions are already known. Okay. let us take a system containing non-degenerate states. So, this is the ground state. For ground state, let the wave function be psi naught. For the first excited state, let it be psi 1. Let us consider this as some nth state whose wave function is n, psi n. Since it is a known system, I will represent the known system with a naught symbol in the superscript. Okay. So, this is psi naught, psi 1 naught, psi n naught. These are all wave functions whose solutions are already available, called known system. And energies of known system are also available. Energy for the ground state, energy for the first excited state, and energy for the nth state. So, these are all already known. Now, our target is unknown system. The given system is unknown system actually. Okay. How the known system and unknown system differs? They differ only slightly, okay, by means of certain perturbation, right. So, what we have to do? We have to apply some perturbation, okay, to the known system, right. This perturbation may be external perturbation or may be internal perturbation. So, if you suppose you take some say hydrogen atom for example. For hydrogen atom, the wave functions and energies are already known. You place hydrogen atom in an electric field. Okay, if you keep it in an electric field, in a weak electric field, then the energies of these states get shifted. Okay, the energy may decrease or may increase. Okay, suppose assume that the energies of these levels increases due to the applied electric field. Let us assume the energies of these states get increases. When the energies changes compared to your known system, then the wave function and the energy of these states, okay, become unknown and we have to calculate that, right. Listen, if you apply very weak electric field or very weak magnetic field, then the difference between this these states and these states, okay, that is the states associated with the unknown system and the states associated with known system will differ only slightly. In that case, we can apply perturbation method. Okay. So, this is the ground wave function for the unknown system. Let me represent that as psi naught. Then for the first excited state, let it be psi 1, and for some nth state, let it be psi n. So, psi naught, psi 1, psi n, and the corresponding energies E naught, E1, En. These are the things we have to calculate. Okay, and these are all known values, right. So, if you want to apply perturbation method for an unknown system, you require a known system which differ only slightly. Okay, so that's the idea. Now, let me introduce what is perturbation method and how to go with the perturbation technique. Right. So, the idea is this. So, our goal is to solve the Schrodinger equation H psi for some state, say nth state, H psi n equal to E into psi n, En into psi n. This is our goal, where psi n is the wave function for the nth state in the unknown system, also called perturbed system. En is the energy of the nth state in the perturbed system, psi n is the wave function for the nth state in the perturbed system. Okay. And what is this operator? It is called Hamiltonian operator for the perturbed system or unknown system. Okay. This Hamiltonian operator for the perturbed system can be given according to perturbation method as Hamiltonian for the unperturbed system, also called known system, plus a correction term which is lambda into H operator prime. Okay. This is what we call as perturbation theory. So, according to perturbation method, the Hamiltonian for the perturbed system can be given as Hamiltonian for the unperturbed system plus a correction term, and the correction term is lambda into H operator prime, where lambda is some parameter. Okay, you know very well parameter, this lambda can take value from 0 to 1. Okay, if you put lambda as 0, then this term vanishes. So, you will left with then H operator become equal to H operator naught. So, your unknown system is nothing but known system. Suppose if you put lambda equal to 1, it means full perturbation is turned on, that is the meaning for lambda as 1. Okay, lambda can take value from 0 to 1. Now, what I am going to do? I am going to apply this formula here. Okay, so in the place of H operator, I am going to apply this here, H operator naught plus lambda into H operator prime into psi n equal to E n into psi n. So, this is the equation we need to solve. Okay, and what I am going to do? In the presence of the perturbation, either electric field or magnetic field or electron-electron repulsion, since the perturbation that we apply is very weak, you can write this the wave function for the nth state and the energy for the nth state, okay, in this manner. See, the wave function for the nth state can be given as wave function for the nth state in the unperturbed system called known system plus some correction terms. Okay, what are the correction terms? Lambda power 1 into psi n power 1 plus lambda square into psi n power 2 plus etc., etc. This is what we call as Taylor series. So, using Taylor series, okay, we can write the wave function for the nth state in the perturbed system as the sum of these correction terms. Okay, this is actually known system and these are all correction terms, and this one is called first order correction to the nth state, first order correction to the wave function of nth state, and this is called second order correction to the wave function of nth state. Like this we can have even many orders of correction terms. Okay, it depends on to what extent to what accuracy of result that you require. Okay. Similarly, the energy of the nth state can also be expanded in Taylor series as energy of the nth state of the unperturbed system, known system plus correction terms lambda into E n power 1 first order correction to the energy of the nth state plus lambda square into E to n plus etc., etc. What is this? This is second order correction to the energy of the nth state. Okay. So, if you substitute this psi n here and this E n here, if you substitute this psi n and E n here, and if you do some mathematical simplification, okay, we will end up with the expression for the first order correction to the energy. Listen, before going further, keep this in mind, this is already known. Okay. What we must know? We must know the correction terms. Similarly, here this term is already known. Okay. So, what we have to do? We have to calculate these correction terms. This is our goal. Okay. So, if you substitute this psi n and E n in the Hamiltonian or in the Schrodinger equation, and if you do some simplification, finally we will end up with this result for energy. The energy of the nth state or first order correction to the energy of the nth state can be given as integral psi n naught star into H operator prime into psi n naught into d tau. So, this is the value we will get, this is the result we will get, okay, if you do the mathematical simplification. Okay. So, what is this? This is nothing but first order correction to the energy of the nth state, right. In a similar manner, you can also find the second order correction to the energy of nth state, third order correction to the energy of nth state. Okay. I will write the expression for second order correction, right. Second order correction to the energy of nth state is equal to we have to take summation m not equal to n integral psi m naught star into H operator prime into psi n d tau square by E n naught minus E m naught. Okay. So, this is the formula we use, or this is the expression we will get if you do that mathematical simplification. Okay. Yeah. Now, see here, this is the second order correction to the energy of the nth state. In second order correction, this numerator value is always positive because we have square here. But what about the denominator? Suppose if the nth state that we are choosing, okay, we are interested on nth state. Suppose if nth state is lower state and nth state is higher state, okay, in most cases we calculate energy of the ground state, okay, right. So, if n is the lowest possible value, then m can take any other value which is above that, right. Therefore, we all know that energy of the ground state is the lowest one compared to energies of the other states. So, lower value minus higher value will give you negative value for this. Therefore, the second order correction term is negative when nth level is lower than mth level. If the chosen state, the nth state, if it is lower compared to m, then this value will be negative. Okay. So, keep this information in mind. Now, what about so this is regarding energy. Now, I will show you how to apply this perturbation method for a system containing more than one electron or some kind of perturbed system. Okay. Yeah. So, let me take a simple example and I will explain how to apply the perturbation method. Remember, before begin with, remember the energy of the nth state in the perturbed system can be given as energy of the nth state in the unperturbed system. This value is already known. Then we have to include the correction terms. Okay. Lambda is a parameter that we are going to fix. So, you need not worry about lambda. We have to include the first order correction, then we have to include the second order correction, okay, etc., etc. So, if you include more and more correction terms, then you will end up with a better result. Okay. So, the accuracy of the result depends on how many correction terms that you are going to consider. But what I will suggest is that if you take first order correction itself for most cases will give 95% accurate result. Okay. So, your result will be almost 95% accurate if you calculate first order correction term. You need not worry about second order, third order correction at all. But for research purpose, you have to include the higher correction terms to get the accurate result. Okay. Now let me take an example, right. Say a particle in one dimensional box problem, particle in 1D box, right. Yeah. Suppose you might have heard about particle in 1D box problem, right. So, let us assume this is as x axis, this point where x is 0 and this point where x is equal to L. So, the length of the box is L, okay, and assume that potential energy of the particle inside the box as 0 and the potential energy outside the box as infinite. Potential energy inside is 0 and potential energy outside is infinite, such that the particle present inside the box, it cannot jump out. So, the particle is restricted inside the box only, right. Now, in this case, how to, in this case you might have derived the expression for energy and wave function, okay. So, these things you know already, okay. I will write the wave function here, we do not have enough space there, so I will write here. Yeah. What is the wave function? Psi n naught can be given as square root of 2 by L sin n pi by L into x. So, this is the wave function for the nth state of particle in 1D box, okay. And here I did not do any perturbation. So, this is a unperturbed system or unperturbed wave function. Similarly, the unperturbed energy En can be given as n square h square over 8 m L square. So, these two are the wave function and the energy for the known system. This is known. Now, I am going to make small perturbation here. See what I am going to do. Suppose suppose if the potential energy of the particle inside the box, suppose if the potential energy increases in this way, okay, at x equals 0 potential energy is 0, but as x increases potential energy increases and reaches some value here, let this value be V naught. So, V naught is the potential energy of the particle at x equal to L. From 0 to L potential energy increases linearly. Okay. So, now I am choosing, I have introduced some perturbation here. Okay. With this perturbation I am going to calculate the energy and wave function. Okay. How to proceed with? I am going to show you only how to find the first order correction to the energy of the system. Okay. So, we know very well first order correction to the energy of the nth state can be given as integral the wave function for the unperturbed wave function for the nth state into the perturbation operator and the unperturbed wave function for nth state into, since it is a one dimensional problem, integral dx. So, we have to calculate this integral so that you will get the first order correction to the energy of the nth state. Okay. So, how to proceed with? Remember, here the potential energy increases linearly. So, that the potential energy, right, this linear increase in potential energy, I am going to take it as perturbation term. So, the perturbation operator for this system can be given as V naught into x by L, x by L. Okay. See, if you put x equal to 0, if you put x equal to 0, you will get H operator prime as 0. That means there is no potential energy at x equal to 0. If you put x equal to L here, L cancels, you will get the potential energy as V naught. Yes, at x equal to 0, potential energy is V naught. And as x increases, potential energy also increases. So, this H operator prime is nothing but the potential energy operator, right, for the perturbed system, right. Now, if I substitute this here and if you calculate, right, I am not going to do the mathematical simplification here. Instead, I will give you the final result. So, if you substitute this here, okay, I will just show you how to substitute. For the nth state, the wave function is square root of 2 by L sin n pi by L into x. Since there is no imaginary term, so psi star and the psi, they are one and the same, into the perturbation operator. Perturbation operator is V naught into x by L into the wave function is square root of 2 by L into sin n pi by L into x. And here the limit for x is 0 to L. Okay. So, root of 2 by L, if you multiply you will get 2 by L and V naught by L, everything is constant. So, you will get 2 V naught by this is L into root L L into L square, okay, into 0 to L sin into sin, and here we have x. So, you will get x into sin square n pi by L into x into dx. Okay. If you do integration and if you substitute that value, finally you will end up with this answer V naught by 2. Okay, V naught by 2. So, the first order correction to the energy of nth state comes out as V naught by 2. If you add this value to the energy of the unperturbed system, this is energy of the unperturbed state. Now, add this value here, okay, you will get the energy of the nth state, which is not exact because you have to include more and more correction terms, okay, to get 100% accurate result, but this will give you almost good result, okay, for the nth state.